Okay, so we are in chapter 9 talking about thermochemistry. So we're going to talk about thermochemistry and something called thermodynamics, and then we'll start talking about what's called heats of chemical reactions. So let's define a few things first before we get started. So thermochemistry is the study of changes in energy that accompany chemical reactions. So we're really going to be talking about energy here in the next few weeks. So it's the study of changes in energy in chemical reactions. One thing is that I will represent change as a triangle. It's the Greek letter delta, and that means a change in. So anytime you see this triangle in front of something, that means that's the change in something. So if you see this triangle and then E for energy, that would mean the change in energy. Also, you'll see me read this as delta. Delta is the Greek letter. It means change in. Okay, so thermochemistry is the changes of energy in chemical reactions. So we're going to talk about some of the different laws of thermodynamics. The first law of thermodynamics says that energy cannot be created or destroyed, only changed in form. So we're going to spend a lot of time talking about this in the next few weeks. So we need to define two different things, which is called the system and the surroundings. So the system is where the reaction is actually happening. I think your book calls it the part of interest. And then there's the surroundings, which is everything else. So we'll come back to this when we start talking about different types of energy changes in chemical reactions. Before we get too far into this, we're going to talk about one type of energy called work. Work is defined as force exerted through a distance. And the formula for that is work equals force times distance. There are some examples that you might see in your SmartWorks homework where it asks you to calculate the work using force and distance. You also might be asked to solve for something called pressure volume work. So solving for pressure volume work is a different formula . Pressure volume work says delta E, so that's the change in energy. I would literally say change in energy equals Q, which we haven't defined yet, but we're going to see that that is the heat of the reaction, minus P, which is the pressure, times the change in volume. Change in volume. So this is a formula that you can use to calculate the amount of pressure volume work that's being done on the system or the surroundings. We usually do this when we're talking about gases that are being compressed, and there are some examples of this in the lecture slides, and also you might see one in your SmartWorks homework, but definitely not going to be the focus of some of the calculations that we're going to spend some more time on later. One more thing that I want to bring up is there's different types of energy. So there's what's called kinetic energy and potential energy. So potential energy is the capacity to move matter, like the energy that's stored in chemical bonds. That would be potential energy. We would abbreviate that E sub P. We'd call that potential energy. This is stored energy. This is the energy in chemical bonds. That's one example of potential energy. Sometimes you'll hear, we'll talk about chemical energy. Chemical energy would be potential energy. Another type of energy is called kinetic energy. Kinetic energy is abbreviated E sub K. Kinetic energy. And kinetic energy is the energy of motion. So in this lecture, in this video, we're really just kind of identifying some of the terms that are going to come up later, and we'll go through those in a lot more detail when we get to those specific parts. Okay, so let's talk a little bit more about heat, which is Q. It's lowercase q. It's the energy that flows into or out of a system because of the difference in temperature between the system and its surroundings. So it's literally the heat of a chemical reaction. And there's two types of chemical reactions that you can have. You can have what's called an endothermic reaction or an exothermic reaction. So I'm just going to make two lists and we'll come back to heat. So this is really important that you understand the differences and what's happening here. So endothermic reactions, this is a chemical reaction or process in which heat is absorbed by the system. So for example, if you were doing a chemical reaction in the lab and you mixed two chemicals together and it was an endothermic reaction, heat would be absorbed. If the heat is absorbed, then that means this reaction vessel would feel cool because the heat is being absorbed. In a reaction where heat is being absorbed by the system, that is endothermic, Q would be a positive number. The heat of the reaction would be positive. So the opposite is true for an exothermic reaction. In an exothermic reaction, heat is evolved. Evolved is just a chemistry word that means given up, given off. Heat is given off. Absorbed means the same thing. It's taken in. So in an example of an exothermic reaction, the reaction vessel would feel warm. Also, in exothermic reactions, Q would be a negative number. So, it's important that you pay attention to the signs of these numbers, positive or negative, because it indicates the direction that the energy is flowing. Oftentimes you'll read a word problem and it's not going to tell you that the heat is a positive number or the heat is a negative number. It might say 100 kilojoules of heat is absorbed. So if 100 kilojoules of heat is absorbed, then that would be positive 100 kilojoules. If it says 100 kilojoules of heat is evolved, that would be negative 100 kilojoules. So you need to be able to extract keywords like absorbed and evolved, or heat is added, heat is removed, to be able to determine what the sign of your numbers should be. And we'll practice that a lot. Another thing you could say about an endothermic reaction is that energy is added to the system. And for an exothermic reaction, it would be energy is subtracted from the system. So this is the basis of what we're going to be talking about. And actually another term that is synonymous with heat is enthalpy. So enthalpy is called an extensive property, and it can be used to obtain the heat absorbed or heat evolved in a chemical reaction. So anywhere you see heat, you could also replace that with enthalpy. And enthalpy is the variable for that is capital H. You'll find that capital variables are what's called a state function, meaning that we don't care the path that it takes to get from the beginning to the end. We're just looking at the initial and the final conditions. So we can't ever really measure the absolute enthalpy. What we can measure is the change in enthalpy. Change in enthalpy. So just like an endothermic reaction where Q is positive, that means delta H would also be positive. It would be a positive enthalpy change for an endothermic reaction. For an exothermic reaction, delta H, change in enthalpy, would be a negative number. Okay, so delta H equals Q at constant pressure. These are the same thing. And we'll never have a situation where we're changing pressure in these examples, so you can always assume that delta H equals Q in all of these reactions. So this is a good introduction. A lot of this might not make a lot of sense right now because we're going to apply a lot of this to specific thermochemical examples coming up in this chapter and the next chapter.